everyone. I'm happy that you noticed that it was on a Monday. I'm happy to see people here. Today we have Vignesh from Indian Statistical Institute, Calcutta, who is going to be talking about fixed point and tilting. Thank you.
Yeah. Thank you. So today's talk is going to be fixed points. Where tilting. So I hope the audio is clear. So whatever I'm going to say today new, that's joined with Robert Burklund. Okay. So in a way, whatever today we are going to talk discuss some methods about how to compute fixed points, cohomology of fixed points through homotopy theory. So when I say fixed points, I should make clear what is the context that I'm talking about, what kind of fixed points. So for today's talk, X will be a finite GCW complex. And whenever we have, and we will restrict ourselves to G a P group. Whenever we have finite GCW complex, we can naturally we can associate to it what's called we can take the fixed points, where this is called the genuine fixed points. The fixed points, and there is a natural question that arises is that if I know enough information, homotopical information about X, can I say something about the fixed points? I mean, this is an interesting question to start and a difficult question because XG is not a homotopy invariant notion. What do I mean by that? If X and Y are two GCW complex and there is a map F which is equivariant, such that F underlying is a homotopy equivalence. This does not imply in general that XG I meant a finite group which is also a P group. So G is a yeah. So if you have an equivariant map, the underlying map is homotopy equivalent. This does not imply that the corresponding fixed points are going to be homotopy equivalent. So there is a natural question: how much can you infer? Given you say you have as much information about the cohomology or the homology of your GCW complex, can you say something about corresponding homology or cohomology of the fixed points? Particularly, like there is something that you can start with. There's a basic observation that you can do. And if G is a P group, you can look at the Euler characteristic of your space X, and you can decompose it into two parts, namely the Euler characteristic of the fixed point plus something divisible by P. So, I mean, you have a cell structure, a GCW complex is obtained by attaching G mod times Sn. Anyways, I'll say it orally. X is obtained by attaching G mod H times Sn. So if you don't have a fixed point, every orbit is going to have be divisible by p, the cardinality of an orbit. So if you split up the Euler characteristic into two parts, you're going to get the Euler characteristic of the fixed point plus something that's divisible by p. So in particular, if you go mod p, you get the Euler characteristic of x is congruent to Euler point mod p. So in this already indicates that you can say something about the relationship between the total space and the fixed points, and the first starting point of answering these kind of questions is done by Smith. So there's a theorem of Smith. So maybe Smith is a very common name in math and also in homotopy theory. This is P Smith. So a G, a P group, and X, a finite GCW complex. This is going to be the setup such that X is a mod P sphere. That is the FP homology is going to be that of some sphere of dimension n. Then the fixed point is either empty or mod P sphere. It's a mod P sphere of a smaller dimension. Dimension less than n. Less than equal to. Less than equal to n. You can also have a trivial action. Okay. So with this theorem as a motivation, and any theorem that starts with the cohomological information of the total space and infers some cohomological information or any homotopy theoretical information about the fixed points to start is called Smith theory, this line of study. And so I should also say maybe whatever I'm going to say new is written up. It's not in archive, but it is in my thesis. Categorification with theory. Yeah. So you can find the proof of the statement that I said today to be in the thesis. So for S1 fixed points, similar kind of stories were also analyzed for S1 fixed points by, maybe I should say that. In the case of S1, there were theorems by Borel, Atiyah, and Bott. In the case of finite groups, there has been work done by Quillen, Moyer, and Wilkerson. The theorem that will be relevant for today is going to be that of Dwyer and Wilkerson. So let me state that. So before that, there is an important theorem in this field called the localization theorem. I'm not sure who I should attribute this to, but this can be found in Quillen's F isomorphism paper. It's called the spectrum of equivariant cohomology, right? It's in the first paper. But let me state this. If G is an elementary abelian group, that is, if G is of the form Z mod P power n, and again X is a finite G complex. Um, so you can start with some information that is homotopical. That is, you can start with the cohomology of the homotopy quotient. This is invariant under homotopy. And there is a map from the cohomology of BG coming from the fibration XG, BG, X. So there is a class here in degree 2 such that so there is a class here. You can pull back the class to get and what Quillen's theorem says is that if you have X elementary abelian group and X a finite GCW complex, you can start with the equivariant cohomology, the Borel cohomology, and you localize it at this Euler class E. So I call this class Euler class. And this is going to be the same thing as the cohomology of the fixed points tensor cohomology of BG localized at E. So this is the localization theorem. I mean, there is a modern interpretation of this. Maybe we'll come back to this later. But people are familiar with Tate construction. This is some sort of Tate cohomology that you can take. And here is the theorem of Dwyer and Wilkerson. Continuing from the localization theorem, is that you can acute. You can acute the Borel cohomology localized with the action of the steel rod algebra, and then they call a certain kind of classes unstable classes. And what they say is if you take the largest unstable module, that is, you pick out all the class by hand, which is unstable, then you exactly get the cohomology of XG times B. That is, you can remove the localization out of the theorem. So why is this? I mean, what is happening here is that once you localize this, it's going to be, you can give this as a module over the steel rod algebra structure, but it's going to be situated in all sorts of degree, both in positive direction and negative direction. And if you want to make it into a cohomology of a space, it puts a certain constraints as a module over the steel rod algebra. In particular, you can identify which classes are stable and which classes are unstable, and you only pick out those classes which are unstable. So, I mean, I'm not going to talk too much about what is this unstable classes. So let me write down this thing. This is the largest unstable steel rod module. It won't be featuring in the main statements that I'm going to say in the talk because I'll give an alternative construction of this functor, which is coherent in all possible way, and which is sort of maybe easier for me to define. So I will not say what is this here, but a good place to look at it is Dwyer Wilkerson's paper called Smith Theory Revisited by Dwyer and Wilkerson. Yeah, so let me leave it at that. Okay, and so in particular, you can recover the cohomology of the space. So what this project that we wanted to answer was, can you recover the entire P local homotopy type of your fixed point? Not just the cohomology, but can you recover the entire P local homotopy type of your fixed points? And this is, so here is the question. Can you recover, one second. Can you recover the P local homotopy type of XG? All right. I'll make sense of. I'll elaborate this question further, or I'll give a recipe today. What do I mean by this? And the answer to it is yes. Using power operations. In particular, we will introduce a notion of perfection in the land of homotopy theory, and using this perfection, we can compute fixed points. So let me get into, I mean, that's enough motivation for like or set up what we are going to deal with. So let's start with, so when X is a space, by a space I mean a homotopy type. We have the diagonal map, which is so we have the diagonal map, and we will also have the, for today's talk, K is a field of characteristic 2. Whatever I'm going to say is valid for other characteristics as well, but I will restrict myself to characteristic 2. So the diagonal map gives you a multiplication at the level of cochains. I mean, this multiplication is only commutative after passing through the homotopy. That is, if you take the cohomology classes only on the cohomology, you're going to get a graded commutativity structure. And this information is, I mean, it actually is not a failure of, I mean, this failure of commutativity is not really a problem for us. It actually gives us an extra structure. So we will exploit that today. So this is what is going to, this has a E-infinity-algebra. So the coaching have an extra structure called the E-infinity-algebra structure. What does it mean is that, yes, when I write xg, I mean the fixed points are what called the genuine fixed points, categorical fixed points, if you want to call it. And if I want to write the the homotopy limit or the homotopy fixed points, I'm going to use this notation for homotopy fixed points. Okay. So the cochains have what is called the E-infinity algebra structure. I don't have much time to sort of briefly explain what is an E-infinity algebra, but shortly it is this. It's a K module. Yeah, that's what I'm going to say is that it's a K module with a bunch of maps So you have for every tensor product n times, you have a map Mn. When I take the tensor product with n time, I can permute the factors. So this n times tensor product is a cube with a symmetric group action. I can take the homotopy quotient. And E-infinity-algebra is an algebra A which has factorizations like this, which has a bunch of structure maps given by, let's call it Mn bar. So it's a collection of all such factorization through the homotopy quotient with suitable compatibility conditions. Let me not get into what these compatibility conditions are, but what does this give? This gives us the follows. Let's pick a class in the nth homotopy group that is giving a map like this. Remember, A is a K module, so we are giving a K module map like this. And then we can tensor it power 2 to get a map from K to N into A tensor power 2. And then we can go further and take the homotopy quotient with respect to the swap action again. So what you're going to get is, let me denote this by 8 sigma 2. So it's going to be a copy of B sigma 2 tensor K to N. You have a map into homotopy quotient. And then because my algebra was E-infinity, I can use this to go all the way to A. This is what I call M2 bar. So this gives me a map like this. So if one observes the left hand side, this is the homology of the group C2, or it's also the homology of RP infinity shifted by 2n. So you'll have a bunch of classes here, and they hit the corresponding classes in the homotopy groups of A. And these are what are called, so you get so let's say, so for every integer I, you get a bunch of maps Qi from pi n of A to pi n plus I of A. And these are what are called power operations. I'm sure that people in the audience might be familiar with it if you have seen what stream dot operations are. For A is equal to the cochains on like over field, cochains of a space over a field K. Q negative I matches with the stream dot operation, and Q sorry, let me say what this is for I I greater than equal to 0, and for Q or I strictly greater than 0, so there is a change in it. And Qi is equal to 0 for I greater than 0. Yeah, so this is what you get for spaces. So that's why you don't see like so-called negative stream dot operations when you learn about stream dot operations for the first time. But this also means that the cohomology of spaces are something special. So what are the properties that this Qi satisfy? Is the first thing is that it's additive. So these are properties of Qi. The second thing is that it satisfies what is called a squaring relation. That is, if you take a class in degree x, it's going to be x squared. I mean, in order to get all these relations, what you have to do is analyze the group cohomology of B sigma B, which we won't do now. I'm just going to list the formula. What's called the Cartan formula. It tells you how you deal with multiplications. And finally, what is called instability relation. So this is Qi of x is equal to 0 when I is less than x. There's one more relation which is you might have seen already, called the Adams relation. It's a bit, let me see if I can get this right. This is sum over k minus j minus 1 of 3 I plus j minus k qk of x. So this also tells us how you can compose two power operations. I mean, it looks complicated. It helps us do some calculation, but for today's talk, just ignore it if you don't want to remember it. So you can create an algebra of power operations. We'll get a better version of this algebra of power operations soon, but you can just form an algebra of power operations like this. Just take the associative algebra generated by, let's say, k qi's, and then you quotient by the Adam relation. That is, this is the associative algebra generated by qi's, and then you quotient it by the Adam relation. So these were this is often called as Dirac-Lashoff algebras, and here is a theorem of Mendel. So I told you that when when we are considering spaces, this is going to be the same thing as usual SQIs, and you know that they are cohomology operations, and then these power operations. And how are these two related? Is that you have the algebra of power operations, and you have an operation called QU. You can consider the two-sided ideal generated by Q0, and you can quotient by this relation by the two-sided ideal. So this is a theorem of Mendel that you can identify this with the Steenrod algebra. So the two-sided ideal, when you quotient it, you can identify it with the P Steenrod algebra. This is true for all prime P, but with this notation, this is for prime 2. If for other primes P, you can quotient by 1 minus P0. Okay. So here is a definition. An E-infinity algebra is perfect. An E-infinity algebra over K is said to be perfect. So, I mean, I was faced with a terminology issue. So I will call this Frobenius perfect, because we use perfect for like perfect modules and like perfect objects in a derived category. I'm also dealing with chain complexes here, so I don't want to confuse. So I'll call it Frobenius perfect, but sometimes I might say just perfect. Bear with me, because it's too much to carry Frobenius perfect. But there is also the notion of Frobenius algebra, so I need to come up with a better terminology at some point. Yeah, so this is an E-infinity algebra over K is said to be perfect if your operation Q0 is an isomorphism. Why do you, I mean, why are we, I mean, why is this deserved to be called perfect? In classical algebra, if you have an F2 algebra, then the operation x going to x square, the Frobenius map, if it is isomorphism, you're going to call your algebra perfect. And this is motivated by this. Say, the assumptions on K for now is that it's a characteristic to field. So yeah, so CA is discrete. K algebra, which is the infinity. I mean, it's a commutative ring. It's an ordinary commutative ring, so it's the infinity. So what are these power operations there? I mean, all the other operations are going to be trivial, but you have one operation that Q0 that goes from A to A. That sends x to x squared. But we know this by a different name, which is the Frobenius map. So this Q0, or particularly all the Qi's together, is like an extension of Frobenius to the land of higher algebra. So what happens is, for a discrete Ki algebra, this Q0 is also an algebra mode. For a discrete. But Q0 from pi star of A to pi star of A is not discrete. Sorry, is not an algebra morphism. So it's not even a map of algebras. So in particular, there is no spectrum level or a commutative algebra level map of Q0 that you can find. I mean, there is a spectrum level map, which we'll talk about later, but there is no commutative algebra map that you can lift Q0 to for some E-infinity algebras over K. So, but I can still talk about what does it mean to be perfect by this definition that I gave. An E-infinity algebra is perfect if this operation Q0 acts by isomorphism. I mean, as soon as we introduce the notion of perfect in the ordinary algebra, there's two things that I can consider. I can consider the process of perfection. Given a F2 algebra or a K algebra of characteristic 2, there are two kinds of perfection that I can consider. So I don't know, I refer to the target as the co-limit perfection and the source as the limit perfection. These have the following universal property. Whenever you have B a perfect algebra that maps into A, there is a unique factorization from the limit perfection. And similarly, whenever you have C, which is perfect, and you are mapping into C, you have a unique map that factors through the co-limit perfection. This is what happens for ordinary rings. You get a factorizations like this. And not only that, we have a formula. I mean, which is why I call this limit perfections and co-limit perfections. The limit perfection is given by taking limit over the Frobenius. The co-limit perfection is given by taking co-limit over the Frobenius. So a part of the story carries over to the world of E-infinity algebra. So let me be quick here that if E is a commutative ring spectrum, by that I mean is if E is an E-infinity algebra in spectra, you can define what is called an algebra operation. This was first defined by Lurie in one of the lectures that he gave on Sullivan conjectures, and it is also a paper by Glassman on Lawson. So it's defined as follows. So how is it defined? So you have the forgetful functor from commutative algebras modules E, over E. And then the functor f belongs to functors from, or you can actually go all the way to spectra. So let's go to spectra. So you have commutative algebras over E to spectra. You have a f here. Note that functors from commutative algebra into spectra is a stable category. So this means you can form the endomorphism of f, and this is going to be an E1 object in spectra. And this is what is defined to be as the algebra of power operation. Why do we call this as an algebra of power operation? Is because for the if I set my commutative algebra to be K, characteristic P field, then the power E is given by the algebra BB that I talked about before, the Dirichlet algebra. And then there is a map into endomorphism of your E. This is identified with, this is an E1 spectrum, so I have to take pi star to talk about an action algebra. And this map is given by the quotienting that we are talking about. Quotient by 1 minus Q0 is equal to 0. So this is the map. Okay. So we have the algebra of power operations. And what happens is that if you consider commutative algebras over K, if there is a forgetful functor into mod K, but actually factors through the modules over power operations. And inside this, I can consider modules over the power operation on which the operation Q0 acts by isomorphism. So, because of this result, that for E is equal to K, the algebra of power operation is the homotopy groups are identified with the Dirichlet algebra. I can talk about I can talk about modules on which Q0 acts by isomorphism. There is an exercise that you can do. I work it out in my thesis that if you could take the multiplicative set that is spanned by Q0 inside the Dirichlet algebra, this satisfies what is called the right OR condition, but it doesn't satisfy the left OR condition. So it only satisfies the right OR condition. This lets you talk about what are called Q0 local objects in the sense of, so this is objects which are local with respect to the multiplicative set spanned by Q0. For more details, you can refer to higher algebra 7.2.3. So there is a section on localization and OR conditions. You can refer to that. But for now, just think of this as modules on which Q0 acts by isomorphism. And you can form a pullback. Commutative algebra scale, which is Frobenius. And this is the subcategory. So this commutative algebra with the Frobenius on the top, FR, is the subcategory, is the full subcategory of all perfect K algebras with the definition that I gave above. So what is the use in defining the category like this is that this pullback can be defined in the category of all presentable categories with right adjoint functors as morphism, PRR. Pullback in PRR. So this first thing that it tells you is that because this is fully faithful, the top arrows also fully faithful, and you get a perfection functor for free. You have category of perfect algebras sitting inside the category of all infinity algebras over K. Because we are taking this pullback in PRR, we are getting one perfection functor for free because it's a right adjoint. And we also know that this category is presentable. Okay. So what we have is that this category, so this is the presentable category. The inclusion accepts a left adjoint. It turns out that it also accepts a right adjoint. This is something that you have to check, and that it doesn't follow from something formal. So you need to show that this subcategory is closed under all colimits in order for you to apply the adjoint property. And for you to say that this is closed under all colimit, you split it up into two different parts. First, the shifted colimits and finite coproducts. And shifted colimits is something that you can deal formally. And for finite coproducts, it comes from the fact that it comes from Cartan's formula. That's how you prove an existence of this right adjoint. So in particular, what you have constructed is for an E-infinity algebra without any formula, two approximations that we had before is that there is a localization and a co-localization with the desired universal property. Whenever you have B perfect mapping into here, you have a factorization. Now up to a contractible choice, but still unique in the infinity category sense. And then you also have a factorization whenever B and C are perfect. So these are the localization and co-localization with respect to Q0 local algebra. But I gave a very nice formula above that sort of is easy to deduce in the classical situation and very useful in computing many things. Can you write down a formula like that for any of these perfections? It turns out that we were able to write down a formula for this. So the thing is, because of this formula, we call this functor tilting. And so the question is, what are the homotopy groups of this tilt? So here's the theorem. So this is.
Sorry, there's a question in the chat. So right vertical is upward.
No. Sorry. Yes. Whatever. Right one. Upward.
Okay.
Yeah. Yeah. Thank you. So yeah. So this is the theorem that if A is a finite type K algebra, then pi star of the homotopy groups is given by the inverse limit over Q0 of pi star of A. Even though Q0 is not a map of E-infinity algebra, or it's not even a map of commutative algebra after you go to pi star, still such a formula holds. This is what you can prove. And how do you prove it is playing around and like spending some time with the Dirac algebra. But the idea is as follows. You're trying to compute the homotopy groups of so this is in mod K of this A tilde. There is a free forgetful adjunction for commutative algebra. So this is same as mapping commutative algebras. The free algebra, this is my notation for free algebra in degree n. This is the same thing as this, as spaces, because commutative algebra is not a stable category. Even though the left-hand side is a spectra, the right-hand side is just a space. And now you use the universal property of perfection. So what you're doing is you're trying to map into the perfect guy. So it factors through the left adjoint. So you will get a factorization like this. So giving a map into the A tilde is the same thing as a map through the perfection. But giving a map like this is also same thing as giving a map in here. So we reduce this problem to calculating maps in commutative algebra of the co-limit perfection of A. And I will not get into what you do here, but I can just say that in this particular case alone, Kn of x is given as the co-limit over, you have a bunch of kxn, it's a free algebra, so I can easily map out of it. So this is given by the map, which is xn going to q0 of xn. So you have to understand what are the homotopy groups of free algebra in degree n, and then you can make, if you know what it is, then this expression will make sense. There is a class called q0 of xn on the target, and you can freely map into it, and you take the filtered co-limit by repeatedly doing this one. So this is in some sense is an analog of x going to x square, but like for like higher degree classes. And now you have this, and this is the idea behind the proof. So you use this to calculate, prove the statement above. So how does it all tie back to what we were talking before? Is this theorem of Mendel. And the statement I'm going to say is it's also, there is a generalized statement by Lurie, but whatever I'm going to say is due to Mendel. If X is a finite type nilpotent space, that is the action of pi1 on the higher homotopy groups is nilpotent, you can recover this space, the P completion of the space, and also let me say that it is P complete. Then you can recover the P completion as a form of global section. So FP bar is some algebraic closure of FP, and you map into FP bar. This is the same thing as XP. So Mendel proves that in terms of simplicially enriched category, but if you take it's equivalently stated as if you take the infinity category of commutative algebras and you look at the mapping spectrum between the infinity rings given here, there is the cochains of X with FP bar coefficient mapping into FP bar. So this is like taking global sections, right? And this is exactly identified with XP completed. I mean, X I assume to be P complete. So let me so this gives you like a p-adic model for spaces. So this is what we will use along with the next theorem. So in particular, whenever we are so this is one theorem, and the observation also is that this algebra is perfect. This is something that you can prove, that Q0 acts by isomorphism. But what is more surprising, this is the second part of the, I mean, like this is the theorem due to Lurie, is that the category that we have defined above, commutative algebras on which Q0 acts by isomorphism, if you take the opposite of this category, this is the same thing as pro P finite spaces. So this is the pro category of all P finite spaces. That is, there is finitely many components, and each of the component is truncated at some degree n. The homotopy groups are truncated at degree n, and all of these groups are P. This is what is finite. It's like pro-finite sets, but an expansion of it. And Lurie gives an approximation to p-adic homotopy theory as follows. So with this, so in particular, whenever we want to say something is a p-local equivalence, we can say that it's enough to give an isomorphism of the corresponding E-infinity algebras. So that's the reason why we went through all this pain to sort of directly to answer our question, can we recover the fixed points? We actually go take the approach of looking at the E-infinity algebras. So let me state the final theorem and finish the talk. So this is the main theorem that if you look at the cochains on, so what is the setup maybe? Let me say this. G elementary abelian, which means G is the product of Z mod P's, but I'm going to state it only for P equal to 2, but it holds much more generality. So you have a localization at a class that comes from group cohomology. This is what is called proper sorry, what is the question? It's not perfect over the sphere spectrum. It is, I mean, it is perfect with the definition that I gave above, is that the Q0 on it acts by isomorphism. That is the definition of perfect for me in this talk. So Q0 is going to be so Q0 in this case is going to be normal Frobenius whenever you take say ordinary rings. So yeah. So this localization that we considered above for in the cohomology group is what is called proper Tate construct. There's some version of Tate construction that comes from genuine equivariant homotopy theory, which basically kills off all orbits G mod H when H is a proper subgroup. Is the same thing as the cohomology of the fixed points tensor with k coefficients again, with the proper Tate construction of a point. Okay. So you have the localization theorem here. So what is the theorem that we prove? I mean, this is not part of the theorem, so maybe there is a lifting of the localization theorem. So I wanted to mention this. But what is the theorem that we have is whenever G is an elementary abelian group and X is a finite G complex, then you take the equivariant cohomology. So this is your recipe. And you take the localization This is going to be infinity algebra again, because state construction is Lax monoidal, or also you're localizing with respect to an element. So it's going to be an infinity ring. But it's not going to be a perfect infinity ring in the sense that what we define. You can apply this tilting functor. This is equivalent to the cohomology of the fixed points times Bg with respect to K. In particular, what I have, I can base change it now. Also, this is nothing special. K, if I base change it down to a field, this is same as cochains of fixed points with K coefficient. So yeah, so this is the theorem that, so you take the proper Tate construction on your cochains, which is given by the localization on the Borel equivariant cohomology, and then you do the perfection, the right adjoint perfection, and you base change it along the map that you get from group cohomology. What you're going to recover is the cohomology of the fixed points. And in particular, you recover the profinite homotopy type of the fixed points. For that, you have to assume that K is algebraically closed. So yeah, thank you.
Thank you very much. So that was